Good morning. My name is Charles Forsberg from the Massachusetts Institute of Technology, and today I'd like to discuss what is the demand for low-carbon liquid hydrocarbon fuels and feedstocks. Let's first take a look at the big picture. Well, the question is, what is the future of liquid hydrocarbon fuels and feedstocks? To address that, I want to address three sub-questions. What do we use crude oil for? Second, what is the future liquid hydrocarbon demand if limit use to where low carbon alternatives are very expensive? Last, can we credibly produce low carbon liquid hydrocarbons from different feedstocks at this scale? I start with the observation U.S. crude oil products are used for multiple purposes. On the right is the traditional list of fuels and other products produced from crude oil. However, I would like to look at it from a slightly different perspective, from the perspective of what is the function of these hydrocarbons. And I list four functions. The first is it's a dense energy source. Second, liquid hydrocarbons are a low-cost energy storage material. Third, these materials are used as chemical feedstocks, a carbon source for multiple products from plastics to drugs to a variety of other products. They are also used as chemical reducing agents, such as conversion of iron ore into iron. In these applications, these feedstocks are not used for energy, but because of their chemical characteristics of the particular compounds that are used. Last, hydrocarbons are used as a radiative heat transfer agent. Now, some fossil fuels are not used for energy production, and I mentioned, of course, chemical feedstocks and chemical reducing agents. What I show here is the manufacturing energy, fuel, and non-fuel, that is feedstock consumption by industry in 2018 in the United States. And I divide industry into five categories. We have petroleum products such as lubricants, chemicals, of course, for plastics, polymers, and other products, metals, paper, food, and a category what I call balance, which is actually miscellaneous activities. The non-fuel components going into each of these industries are shown by the black arrows below. The chemicals, we have chemicals that are, I should say hydrocarbons that are used as fuel and hydrocarbons that are used as the feedstock. Those are the two colors in red. The color on the right is the feedstock use, which is larger than the fuel use. Now, the total input is 19.4 quads of energy. However, the non-fuel component is 6.1 quads. In short, 6% of U.S. energy consumption is for non-energy use. And that translates into the equivalent of 2.4 million barrels of oil per day. Let's look at the second application of liquid hydrocarbons, that is transportation. And I'd like to start with aircraft and heavy trucks. Now, aircraft and heavy trucks have high penalties for alternative fuels. And the reasons are twofold. First, an added kilogram of fuel or engine implies one less kilogram of cargo. This includes heavy trucks because we have weight limits for trucks on the road. Second, jet and diesel fuel use oxygen from the atmosphere to oxidize the fuel. There is no weight penalty. In contrast, if we use batteries, the batteries contain the fuel and the oxidizer. You have the weight of both, which is why, of course, they have a much higher weight penalty than hydrocarbon fuels. Now, the fuel consumption for diesel and its related products is about 3.8 million barrels per day. Jet fuel consumption is 1.1 million barrels per day. And in particular, jet fuel consumption is increasing significantly with time. Significant uses of liquid fuels. Let's turn to the other side of the liquid fuel transportation demand. Cars and light trucks, that's gasoline. About 8 million barrels per day of crude oil are used to produce that gasoline. Now, light vehicles have very different constraints than jets or heavy trucks. The primary owner cost is the vehicle, not the fuel. There are massive impacts on the bottom 60% of society if we have high-priced vehicles. And the reality is that non-hydrocarbon fuel, all electric vehicles are expensive. Let's go into this in a little further detail. Internal combustion engine vehicles are cheap because they're made of low-cost, abundant steel and plastic, cheap materials. Electric vehicles are expensive because the batteries are made of expensive, non-common materials, such as nickel at $30,000 a ton and going up, and lithium at $13,000 per ton and going up. There is no way we can make low-cost electric vehicles unless there's a radical change in battery chemistry. Now, there are other implications of all-electric vehicles. An all-electric vehicle fleet could raise electric prices for everyone. People buy cars for assured transportation. All-electric cars increase the peak electrical demand. We see this in the right, which shows the impact of electrical vehicles on electricity demand in California over a period of 24 hours by the addition of electric vehicles. And what happens is electric vehicles add additional demand early in the evening. That's on top of the peak demand of the day. People want their cars recharged so they can be used. Bottom line, an all-electric vehicle will increase electric costs for all customers because of this peak demand effect. Let's look at this in a little further detail. Peak electricity demand drives the total cost of electricity for everyone. 40% of the cost of delivered electricity is in transmission and distribution, as shown in the pie chart on the right. This is the total cost of delivered electricity to the consumer. The blue is the cost of generating that electricity. The green is the cost of the local distribution system. The orange or brown is the cost of the transmission system. A big chunk is in delivery charges. Now, if all electric vehicles, we increase the peak demand that could double the cost of electricity for everyone from distribution and transmission upgrades. The system is very sensitive to the peak power demand. In contrast, if we have plug-in hybrid electric vehicles, that is batteries plus fuel, we can lower electrical costs by recharging at times of low electricity demand. And that's because we have the liquid fuel that guarantees we have a vehicle that can be used at any time. The dual fuel characteristics can drive down the price of electricity. Where does that leave us? That leaves us to the conclusion that hybrids and plug-in hybrids are probably the light vehicle future. Now, of course, as you know, today we're primarily gasoline with internal combustion engines. There's a lot of work on hybrid-fueled vehicle options, but a lot of uncertainty about that. If we have hybrid vehicles, the internal combustion engine, and a small battery, liquid fuel consumption will go down by a third. If we have plug-in hybrid, internal combustion engine, and a somewhat larger battery, and only recharge when the grid has capability or capacity, the liquid fuel consumption will go down by 2/3, and we may reduce the cost of electricity for everyone by more efficient use of the electric grid. In contrast, the all-electric scenarios result in increased vehicle costs and increased electrical costs. What that implies is that a hybrid or a plug-in hybrid option would use somewhere between 2 and 3 million barrels a day of gasoline versus the current 8 million barrels of gasoline. With that, let us now turn to radiative heat transfer, another demand for liquid fuel. Now, we have built into our society other needs for liquid hydrocarbon fuels, and I'm going to describe one of these. Many high-temperature processes require radiative heat transfer from energy source to the product. what I call the campfire effect. It's the carbon in the fuels that provides the radiative heat transfer. If you burn hydrogen or electrically heated hot air, you do not provide radiative heat transfer. The flames are invisible. I show in the picture on the right, of course, a blank box. That's what you see if you're burning pure hydrogen or heating hot air. There's no significant radiative heat transfer. You're not going to get burnt standing close to it. The question is, what replaces carbon in these high temperature processes to enable heat transfer? I don't have any simple answers for that, but it's one of the questions that has to be addressed. But it raises a second question. What other requirements for carbon fuels have we built into industrial processes that we don't realize are in those processes? We have used fossil fuels for so long that we may be in a situation where we have lots of uses where we cannot use the obvious alternatives because the fossil fuel provides multiple functions. With that, I'd like to turn to the wild card. Will we need hydrocarbon liquid fuels to replace the storage function of natural gas? Now, the U.S. requires millions of gigawatt hours of energy storage to address daily to seasonal energy storage. The primary storage technology is natural gas. On the left, I show the proposed or the base case EIA business as usual electricity generation for an average day in the year 2050 over a period of 24 hours. And it shows different types of generators: solar, wind, natural gas, nuclear, and coal. What is noteworthy is that the demand, or to meet the variable demand for electricity, the primary swing fuel is natural gas because it is storable. Similarly, if we look at the seasonal demand for energy, which is shown on the right in 2020, what we find is that the green shows the monthly demand for electricity, and the blue shows the monthly demand for natural gas. And we see peak demands in January and December to meet heating loads. So the question is, what happens if we eliminate natural gas and the storage function it provides? If it's liquid fuels, it's a major additional demand. With that background leads to several conclusions. First, if we never had crude oil, we would have invented liquid hydrocarbon fuels and produced them from other feedstocks. They're absolutely remarkable materials, which is not generally appreciated by our society. Second, there's a high-cost U.S. society of produced less than 10 million barrels of liquid hydrocarbon fuels. Third, the future demand could be as high as 20 million barrels per day if we partly replace the energy storage function of natural gas. Now, current consumption is about 18 million barrels per day. This leads to a second set of conclusions. At this scale of hydrocarbon demand, limited number of low-carbon liquid fuel production options. The main option is cellulosic biofuels made with massive external heat and hydrogen input. It's the lowest cost option, and there is sufficient feedstock to replace liquid fuels. The second option is hydrocarbons made from natural carbon dioxide sources. That means air or water. That is a much more expensive option. The third option is to continue to use crude oil with massive negative carbon emissions strategies. So the bottom line is the real world requirement for low carbon liquid hydrocarbon fuels on a massive scale. It is unavoidable reality, and it implies the need to seriously think about how we're going to produce those liquid hydrocarbons to replace crude oil. With that, I will stop and open the session to any questions from the audience on the presentation today. Thank you very much.